Okay, so now we're on the second page of our Chapter 6 class examples. Let's talk about scoring the decathlon. Silly example, but suppose two competitors tie in each of the first 8 events. In the 9th event, the high jump, one clears the bar 1 inch higher. Then in the 1500 meter run, the other one runs 5 seconds faster. Who wins? It boils down to knowing whether it is harder to jump an inch higher or run 5 seconds faster. We have to be able to compare two fundamentally different activities involving different units. Standard deviations to the rescue. If we knew the mean performance by world-class athletes in each event and the standard deviation, we could compute how far each performance was from the mean in standard deviation units, called z-scores. So consider the 3 athletes' performances shown below in a 3-event competition. Note that each placed first, second, and third in an event. Who gets the gold medal? And who turned in the most remarkable performance of the competition? So the first thing we have to do is think about all of the things that are going on in these 3 events. We have a 100-meter dash, which is measured in seconds, a shot put that is measured in feet, and a long jump that is also measured in feet. These are different units, so we want to convert them all to z-scores so they no longer have units. Z-scores are always distance from a mean. Okay, so we also have to think about, in a 100-meter dash, more seconds means it took you longer. So a bigger number here is worse, but in shot put and long jump, bigger numbers are better. So when we think about this, we have to take that into account. Another thing we need to take into account is if we look at our units, this is in feet and inches, so we have to realize that 27 feet 3 inches is 27.25 feet, or you could turn it all of them into inches, but then you're working with larger numbers, but that's up to you. Similarly, here the mean is given in feet. Here the standard deviation is given in inches. 6 inches is half of a foot. So there's a lot that we had to think about before we could start doing this problem. Now, we're looking at competitors A, B, and C, and we have these different events. So this, being big, is bad, so we want the opposite of the z-score here, because that would be how much better it is. Shot put, positive is good, and long jump, positive is good. So we're going to calculate the opposite of the z-score here, the z-scores for here and here. Okay, so we've got competitor A. In order to calculate a z-score, I'm going to start with the long jump just because it's easy. It's an easy calculation, and I'm just going to go backwards. So if we do the z-score for the long jump for competitor A, it says up in the table above that is on your paper but not visible here, that, here it is, his jump was 26 feet. Okay, so the z-score would be 26, the length of his jump, minus the mean. Well, the mean is also 26, divided by the standard deviation, which is 0.5. 26 minus 26 divided by 0.5 gives you 0. So he performed exactly at the mean. So now we're going to calculate his z-score for the shot put. So we're going to do the same thing. We're at competitor A. His shot put throw was 66 feet. Minus the mean shot put throw is 60 feet divided by the standard deviation, which is the 3 feet. 66 minus 60 is 6. 6 divided by 3 gives us 2. So competitor A's shot put performance was 2 standard deviations above the mean. So 2 standard deviations above average. Okay, so then with the 100-meter dash, more is not good, so we want the opposite of that. So we're going to calculate the opposite of the z-score. So in this case, we're going to want the opposite of the z-score. His speed is 10.1 seconds. Minus the mean, which is 10 seconds, divided by the standard deviation, which was 0.2 seconds. So in here we have 0.1 divided by 0.2, which is going to give us 0.5. But we want the opposite of 0.5. So his speed was 0.5 standard deviations above the mean, but that would be a bad thing, so we want to bring his score down by half of a z-score. Okay, so his performance was half of a standard deviation below the mean. Okay, so if we go through and we do this process for all of these athletes, you should go through and do these and make sure you're able to get these numbers. This one's 0.5, this will get you a 0, this will get you a 2, this will get you a negative 1.5, this is a 1, and this is a 2.5. Okay? So if we want to come up with who gets the gold medal, which was the first question that we're asked to figure out, we would add up their performance in each of the 3 categories without units, because now we have z-scores which don't have units. We have 2 plus -0.5 would give us 1.5. So overall, competitor A performed 1.5 standard deviations above the mean. Competitor B, 2 plus 0.5 is 2.5. And competitor C, we have a negative 1.5, a positive 2.5, and a positive 1. That gets us 2 standard deviations above. Okay, so overall, competitor B should get the gold. The second question says, who turned in the most remarkable performance of the competition? So even though competitor B won overall, the most remarkable performance is this 2.5 standard deviations above the mean. And that was competitor C in the long jump. So competitor C's long jump performance was the most remarkable performance of the competition.